Okay, so recording started. I hope you are able. And also during the presentation or during the entire webinar, feel free to interrupt me and ask questions if you have any. So without further ado, welcome to Introduction to CDT webinar here on the 10th of June. So the plan is that we'll have this presentation where I give a introduction to machine learning and the Vidometer classifier design tool. And that should take around 10-15, followed by a demo in the actual software, which will take perhaps 15-20 minutes. And following that, we can have questions if there's any after that. So here's the overview of this presentation. So we'll begin off with asking the question, what is machine learning? And how can we use, or what can the classifier design tool CDT be used for? And how do models actually create predictions? What is the machine learning workflow? What are features and why are they important? And what are the major subdivisions in the field of machine learning? And how is model performance measured and estimated? And then finally, we'll have a short series of demos in the actual software. First of all, we have all probably heard these buzzwords of AI and ML and DL, so artificial intelligence, machine learning, deep learning. But what do they actually mean? If we start at the very top, then artificial intelligence is the field of study where systems that can mimic one or more parts of intelligent behavior. So it's quite general, and not all machine learning algorithms which you hear about, or all machine learning algorithms, which is the next subdivision, they are AI algorithms. But you can find many examples of algorithms that are AI, but not machine learning. So what is machine learning? Machine learning is then AI systems that can improve. So they have this kind of learning property. So they can actually learn from data. And then for your interest, deep learning is then the this subset of machine learning in which you use these models called deep artificial neural, which can learn from data. So a short overview of machine learning. So what do we do at Vidometer? So first of all, there's 3 major subdivisions of machine learning. And the first one is supervised learning, where you can subdivide it into classification and regression. And the reason why it's called supervised is because we as people tell the machine, this is a good seed, this is a bad seed, or this is a dog, this is a cat, and so on. And the machine will then how to actually classify them. There's also another field called unsupervised learning, where we do not provide any labels. We just put the data into the algorithm and it learns by itself, for example, how to cluster. So there's also another field used for various different kinds of applications. So, but we use classification. So, and for example, you can use it for classifying rice seed or cereals or any other kind of classification you can think of. So here's an overview of the machine learning workflow. So how we actually go from just seeds and imaging them to producing a model which we can use then in production environments. And the first step is data processing. So we would retrieve data by capturing an image. And I think all of you have been to the other webinars where we explained that do a transformation and a segmentation and so on. So that would be those steps you follow first to get the blobs out. And once you have gotten this data out, these blobs, you would then label them. And also a particularly important step is then to actually pre-process the data, so cleaning it and exploring the data. And after this step has been completed, you would move on to the modeling step, where you would select that you use to discriminate between the various classes. So, for example, you might have a good seed and a bad seed, and maybe the difference between those two, what makes a good seed good and a bad seed bad, would be the color difference. So once you have selected these appropriate features, some other data that you're not trained on, and when you're happy with this performance, you move on to deploying the model in a production environment. And you then monitor and update the model with new data as you see fit. And then you actually go through this entire process again and again until you converge to a model that you are satisfied with. Okay, so the next major topic. So I said feature a lot, and the classes is based on the features we have chosen for it. But what is a feature? And the answer to that is a feature is some kind of measurable property or characteristic. So it could be the shape, the size, the color, the texture. Property which we can use to distinguish between them. And in CDT, so the classify design tool, we have a large selection of these features to choose from. Consider the case here where we have maize, wheat, and rapeseed kernels, and we would like to distinguish between those classes. It could be that so then we could choose, for example, among shape features, the compactness or how pointed they are. You could area, length, the width, and so on. Or you could also use the color features. But once you have selected relevant features, you would then go on to the step of training the classifier. So in this next slide, we sketch out prediction. So when the classification occurs. So the first steps here are what we showed in the previous slide. So you have some labeled data. A person selects features, trains the classifier. And once you have a trained classifier, it might be that you have some new unlabeled data. So you then use the model to produce predictions. That is what you get out here. So correctly predicts this broken maize as wheat. And there's an important lesson here because in the training data at the beginning here, we did not include any broken maize. So, and the model lives in this world where it has only seen. Therefore, this is one explanation why the model actually failed to find this broken maize as maize. Another explanation is that it could be that we just selected the wrong features over here at this. But this is a very important lesson to when you do modeling. Next, we talk about how we actually do modeling here as Videometer, or which kind of models we use. And we talk about these kind of decision trees, and we also talk about what are decision boundaries. So imagine the case where you have these three classes again, and you have chosen two features, so versus area, and now you would like to create a prediction model. So where you can give it new domains. And how you can do this with a decision tree is where you ask a series of questions. So here you ask, is the area then it's maze? If yes, then you move on and ask a second question. And here you ask, is the compactness less than 0.5? Then it's OSR. If yes, then it's wheat. So you follow this sequential decision-making process until you arrive at one of these three nodes. So how are predictions then made? So, and more specifically, if I now go out and I get a new point, so I get a new seed and I measure the area is 37.5 millimeters squared and the compactness is class to measure predict and why. And the answer is that since this point falls within the OSR region, this one is predicted as OSR. So moving on to you can say the case was, so we just saw what happens when new data points are found, and it might be that we have now found 6 new seeds we would like to classify, and they are giving the following predictions that you see here, where I color coded green as it's within the correct prediction and as incorrect. So clearly our classifier is doing something well, but it's also making a few mistakes. So how do we actually improve it then? And the answer is that we would use this data to retrain the model, and you would then move these decision boundaries to something that is more close to the actual underlying population. So, and here we hope that we have acquired sufficiently many data points so it reflects the underlying population. So we have more trust in our model. Then we move on to asking the question, so how do we actually quantify good or bad a model is? This is a very important topic in machine learning because we need to quantify performance. We need to know how good or bad it is. And the way we do that is that we use a tool which is called a confusion matrix. And it is a tool for visualizing and summarizing the performance of the model. And practically, it is a table of 2 dimensions, which shows the actual and predicted. And the reason why it's called a confusion matrix is because it makes it easy to see if a model is confusing the classes. And I'll get back to what this means in a few slides. There's also 3 important concepts to keep in mind. So there's the training, validation, and test set. And these are data sets that are used in the context of training and assessing the performance of a model. And finally, we use a specific method when you do not have a test set, which is called 5-fold cross-validation. And I'll also get back into what this means. But from a high level view, this is a method for estimating performance when there's no test set. And the idea is that you subdivide your training data set into 5 equal parts. Then you sequentially leave one out, train on the rest, and record the predicted classes. And you do this 5 times to get through all 5 splits. So first I'll explain what a confusion matrix is. And as you can see here is a 2-dimensional, so it's a table of actual and predicted classes. So the rows here will represent all the classes that are actually A, But the first row will be all the ones that are actually A. The second one is all those that are actually class B. And then the columns are the predicted classes. And moving on to the concept of sensitivity and specificity. So you could call class A and B positive and negative respectively. And then in this case, you would measure the true positives and the true negatives. And for the mistakes, you would measure the false negatives and false positives. And from this table, you can then get the measures which are called sensitivity and specificity, which are also known as the true positive rate and the true negative rate. So here is a practical example. So consider the case where we are trying to train a machine learning model to predict whether a seed is healthy or damaged. And we will consider the damaged class as the positive and the healthy as negative, and consider the case where we have 300 healthy and 300 damaged seeds. Then we observe that the true positive rate is 50%. So in this case, we see that given 300 seeds, it will predict 50% as damaged and the other 50% as healthy. But of all the 300 healthy seeds, you see that the error will be much lower and the accuracy will thus be much higher. So from this table, you can observe that the model has bad performance on damaged seeds because it has a low sensitivity of 50%, but it has a good performance on healthy seeds. So what we can now, the story here is then that we need to look further into why it has such a hard time classifying the damaged seeds. It's obviously doing quite well when we present it with a healthy seed, but we need to do more work on actually finding the difference between the damaged and healthy seed. So moving on to explaining training, validation, and test sets. So you can consider the case where we have the entire data set here, and then we could subdivide it into training, validation, and test. So in general, it is recommended that the training set is about 60% of the data, validation is 20%, and testing is also 20%. The training set is used by the model to actually learn the task, so to fit the parameters of the model. The validation set is used to determine the best higher parameters. In general, you can see that these two are often fused if you do not tune the higher parameters. And then the test set is the independent test set which you kind of log away until you're done with training, and then you test how good the model actually is. And finally, we talk about cross-validation. So in the absence of a test set, you still need to estimate the performance of your model. And one way to do this is that you have your entire data set and you subdivide it into 5 equal parts. And for each, what we call fold, you leave one out. And that is now considered the test set for this fold. And the rest is considered the training set. So you would train one model using only this 80% part of the data. And then after that, you test on the odd one out. And you do this 5 times. You record all the predictions. Then you construct the confusion matrix. And again, this is a very good method, but in general, it's always advised to have a test set instead of using cross-validation. But if you don't have that, then cross-validation is your best answer. And the last few slides, we provide some examples of models that were made in CDT, so what you could potentially use this software for. Here we have a simple model where we want to predict either good or discolored maize. So as you can observe here, these maize kernels, they have some kind of discoloration, either a small patch, or maybe the entire kernel is discolored, as you can see here. And we would like to predict if that is the case. So this is one example where you would use color features. There's nothing about the shape here, it's only about the colors. And another color example, here we have a rice color classifier. And for each row, you have a new class. And starting at the top, you have the black class, then the brown, then the purple, the straw, and the white. And you can also see the classes here and this column here. And again, it's a color classifier. So again, we would apply color features. And here on the right, you see the five-fold cross-validation results. So you see there mostly it's going quite well, but there are a few mistakes, as you can see here. And that's good information that we then use to improve the model more. And here we also have another color model. So same principle as before. Here it's just for cowpea instead. And the last one we show is the spinach model. So here it's a bit beyond just using color features. Here you would also use different kinds of shape, maybe texture features as well. And here you have these kinds of classes, so cereal, spinach, cleavers, and so on. And here again you get the performance. And here again you can actually use these numbers to find out which classes are being confused with each other. Okay, so that was the entire slideshow, and the short summary is that AI or artificial intelligence covers, but is not limited to machine learning, and machine learning covers, but is not limited to deep learning. And creating a machine learning model is an iterative process. So you try something, you make some experiments, and you test something out, and you do this over and over until you are satisfied with the result. And the way these algorithms actually work is that they learn how to subdivide this space of features into distinct regions, and then points in each region correspond to a single class. And as you just saw, the classifier design tool can be used to solve many different problems, such as color models or spinach models, cereals, OSR, and beyond. Are there any questions before we move on to the demo? Okay. I'll just stop recording.